Okay, so let's continue with the next topic, the integral of a composite function and the chain rule. Now, for this topic, we try to use the next theorem that we will be discussing, theorem number 2. So we have the statement: if f of x is an antiderivative of f of x, the small letter f of x, and u is a differentiable function of x, then we have the following expression: the integral of the form f of u du over dx, dx is equal to the integral of f of u du is equal to f of u then plus c. Now, it gets more complicated because your expression for the integrand is composed of several distinct expression, so which makes it a composite function. Now, if you're given a composite function as part of your integrand, we try to simplify it by representing one of the expression in terms of the other, and the derivative in terms of the other. So to do that, let's take the following examples. Okay, so example number 1, you are given the integral of x cubed plus 2 raised to 3, multiplied by 3x squared dx. Okay, so the idea here is to represent one expression in terms of the other and finding the derivative. Hopefully that the derivative will result into one part of the expression. In this case, we let u equal to the expression x cubed plus 2. Then finding the derivative of u, the derivative, of course, using the power formula for derivatives, what we do is that we bring down 3 beside your x, so this becomes 3x, and we subtract 1 from your exponent, so 3 minus 1 becomes 2, then derivative of x. Now, notice that the resulting derivative, 3x squared dx, is actually part of your integrand, which is 3x squared dx, this one. Now, so that means this is actually your du, 3x squared dx, that is your du, and your original expression x cubed plus 2 is actually your u. So meaning your original composite function can be written down in the form of integral of u raised to 3 du. This one. Since u here is your x cubed plus 2 and your du is your 3x squared dx. So your original function x cubed plus 2 raised to 3 is your u cubed, and your 3x squared dx is your du. Now from here you are left with the integral of u raised to 3 du. Now from here it follows that you will be applying the power formula for the reverse antidifferentiation. So in order to get the answer, you simply make use of the pattern. So the pattern goes with u raised to 3 plus 1 over 3 plus 1, then plus c. Of course, this results into u raised to 4 over 4 plus c. Now, doing the substitution again for u, since u originally is your x cubed plus 2, we could replace u with your original expression. So this would be x cubed plus 2 raised to 4 over 4 plus c, or that would be 1/4 x cubed plus 2 raised to 4 plus c. Now, although this is somewhat simpler in terms of representing one expression of the original integrand in terms of the other, but the difficulty here lies with which part of your integrand will you be representing in terms of u. Now, this would be the suggestion. The suggestion is you look for the part of the expression as part of your integrand having the highest of exponent or having the highest power. Obviously, in your expression x cubed plus 2 raised to 3 and your 3x squared, between cube and x squared, you have 3 as the greater power. So that would give you a clue in which part of your integrand will you be representing as your u. So once you have decided which part of your integrand would be u, then you could proceed with finding du. Hopefully that the resulting derivative of your expression would result into the derivative of the part of your integrand which is equivalent to du. Now let's try to do the same process for example number 2 for integral of cosine 3x dx. Now, of course, in your expression, this is a trigonometric function, whereas your example number 1 is an algebraic function. Now, if you're given an algebraic function, your clue is simply to look for the highest exponent, and you represent the expression under that exponent as your u. Now, for in the case of the trigonometric function, in this case, cosine 3x is cosine 3x dx. Normally, what we represent as part of as our u is the angle for your given trigonometric function. In this case, 3x. So if we do that, we let u equal to 3x. We get the derivative of u, so that would be du. Derivative of 3x is 3 dx. Now, of course, in your original expression for the integrand, you do not have 3 dx here, but you only have dx. So what we can do is to solve for dx in terms of du. So since you have du is equal to 3 dx, dx can be solved as du over 3. So replacing all the expression in terms of u and your u and du, our original integral cosine 3x dx becomes integral of cosine u du over 3. Now, 3 over 3 or 1/3 here is a constant, so based on the properties of the indefinite integral, all constants can be written outside of the integral sign, so we can have this as 1/3 integral of cosine u du. Now, of course, what was left in the process is that we get the integral of cosine u du. Now, of course, this is a trigonometric function. In order to get the answer for the integral of a trigonometric function, you go back with your definition for the derivative of the trigonometric function and doing the reverse process. Of course, integral of cosine u results into sine u plus c, resulting into 1/3 sine u plus c. Replacing u with your original expression for the representation of u, which is 3x, so we have now the final answer as 1/3 sine 3x then plus c. Most of the exercises and the items in the exams that you will be encountering, you expect that you will be doing the same process here based on these examples. One for this form and the other one is of this form. Now let's have another example. Let's have number 3, integral of 2x over x squared plus 1 dx. Now again, this is an algebraic function. So just like what we did in the first example, which part of the integrand you will be using, you will be representing in terms of u, the suggestion is the expression with the higher exponent. So in this case, in the example number 1, just like what we did, is that choosing between cube and square, so we choose cube since this is the higher exponent. The expression under cube is x cubed plus 2, so we represent u as x cubed, we represent x cubed plus 2 as our u. Now, doing the same for example number 3, of course, between 2x, x has the exponent 1, and your denominator x squared plus 1 has the higher exponent, so that is square. Therefore, the expression x squared plus 1 would be our u. Now, remember to include all the expression in your denominator since you only have the terms to choose between the numerator and the denominator. So, between the numerator and the denominator, we have the whole denominator to represent as your u. So we have now u here as x squared plus 1. Now the derivative of u is du, the derivative of x squared plus 1, doing the power formula or the chain rule or the power formula for finding the derivative, you bring down 2, you have 2x and you subtract 1 from your original exponent. So 2 minus 1 becomes 1. So your expression here for the derivative would be 2x dx. Of course, plus 1 here no longer appears in your derivative because this is a constant. The derivative of a constant, try to recall in your differential calculus that the derivative of a constant is 0. So that meaning the derivative of 1 becomes 0, so this is supposed to be plus 0, but that no longer appears in your expression, so you are left with 2x dx. Now, having to replace the representation for u and du in your original expression, 2x over x squared plus 1 dx, we can write this down as actually in the form of, since you have 2x and dx here is part of your numerator, we can write down this as 2x dx. Now obviously 2x dx from your representation is your du, so meaning this is in the form of integral of du, and your denominator is x squared plus 1, and your x squared plus 1 is your u. So you are left now with the representation integral of du over u. Now recall that this form integral of du over u results into ln of u. Now how did we arrive with ln of u? Try to recall the definition for the derivative in your differential, the derivative of ln of the form of ln u in your differential calculus. The derivative of ln u is 1 over u derivative of u, or if we try to make use of x, the derivative of ln of x is dx over x. Doing the reverse process of anti-differentiation, the integral of the form of du over u or dx over x should result into ln of u or ln of x. We're talking about patterns. For du over u, ln of u, or dx over x, ln of x. Now, that leads us to the answer for the integral of du over u, which is ln of u plus c. Again, to go back to our original representation in terms of x, now we replace u with our representation of x, which is x squared plus 1. So, meaning our answer for ln of u plus c becomes ln of x squared plus 1, then plus c. Again, the highlighted expression is our final answer for our example. Okay, again, let's proceed now with example number 4. So, example number 4 is again a trigonometric function. So you expect that whenever you encounter examples wherein you are asked to get the integration of the trigonometric function, you try to recall the definition of the derivative of the function in your differential calculus. Again, let's go over again with the definition for the derivative. The derivative of cosine is the derivative of sine is cosine. The derivative of cosine is negative sine. Therefore, the reverse process or the antidifferentiation of the trigonometric function for sine and cosine, again, the derivative of sine is cosine. Therefore, the integral of sine is the integral of cosine is sine. The derivative of cosine is negative sine. Therefore, the integral of sine is negative cosine. If you didn't get that based on the audio and the video, try to look for the definition again in your notes or in books on differential calculus. Okay, so let's go over with example number 4. Integral of negative cosine x square root of sine x dx. Try to notice the arrangement of the terms in your given function or the integrand. The only term inside your radical or the square root is sine x. Dx is outside of the radical. Now, try to recall in our first example number 1, the same goes with what we have done with example number 3. Choosing between which part of the integrand will you be representing as your u, the clue or the suggestion is which part of the expression has the higher exponent. So in our example number 1, the expression x cubed plus 3 has the higher exponent as compared to the expression 3x squared. So we choose x cubed plus 2 hours our u, since this expression has the higher exponent as compared to x squared. Now, in our expression negative cosine x and sine x, recall that the square root is actually expressed in terms of power as 1/2. So our square root of sine x is actually sine x raised to 1/2. Now, cosine x here has no exponent, has no power. So meaning it has only a power of 1, as compared to sine x, its exponent is raised to 1/2. Now, try to compare that with what we have done with example number 1. What we have chosen as our representation for u is the higher exponent, but in this case 1 is the higher exponent instead of 1/2. But of course, obviously, what we have done here is that our expression for u, or our representation for u, we have chosen sine x instead of cosine x, noting that the exponent of cosine x is the higher exponent as compared to the higher exponent, which is 1, as compared to 1/2 for sine x. Now, let us try to generalize the suggestion of which expression or which part of your integrand would you represent as our u. Now, so meaning between exponents other than 1, so for example in example number 1, choosing between cube and square, you choose the higher exponent. Now, between any expression except 1, for example, in example number 4, choosing between 1 and 1/2, you choose 1/2. So instead of 1. So meaning, this is a suggestion, and most likely this representation would result into a less complicated solution as compared to choosing over 1 as your the expression under 1. So between 1 and 1/2, you choose 1/2. This is the suggestion, and that would most likely result into a simpler solution as compared to choosing over the expression under 1 as the exponent. Okay, so try to take note of that. So meaning between cosine, which has the exponent 1, and sine, which has the exponent 1/2, we choose sine x, since this is the more complicated exponent. So generalizing the idea for choosing which expression that we will be choosing to represent as your u, you choose the more complicated exponent. So between 1 and 1/2, 1/2 is the more complicated exponent. Between 3 and 2, meaning between cube and square, cube is the more complicated exponent. So the idea here is that the solution follows a deductive pattern, meaning from general to simpler, meaning from more complicated solution to a less complicated solution. Okay, so try to take note of that. So let's now go over with the solution for example number 4. So we represent u is equal to sine x, and of course derivative of sine x is cosine x, derivative of x. Now, try to notice our representation, our original expression, integral of negative cosine x, square root of sine x dx. We could replace sine x here as your u, since we have done the representation. So meaning, since our sine x is sine x raised to 1/2, that becomes u raised to 1/2. Now, in our second intervening step, I have written down the original expression, or rearranging the terms accordingly, as negative sine x raised to 1/2 cosine x dx, attaching cosine x to dx. I have done so because try to note that the result du uh, is equal to cosine x dx. So meaning if we attach cosine x with dx, that would represent actually our du, just like here. So meaning this arrangement, negative sine x raised to 1 half cosine x du, can be written down in terms of the representation of u du as negative integral of u raised to 1 half du. Now, of course, negative here, which is originally inside of the integral sign, is written as outside, since obviously negative here is negative 1, so negative 1 is a constant. Negative 1 can be written outside of the integral sign as negative 1 or negative integral of u raised to 1 half du. Now, finally, you are left with u raised to 1 half du. Now, just like what we have done with in the previous examples, this form u raised to 1 half du is of the form of the power formula. So in order to perform the integration for the power pattern, we make use of the pattern u raised to n plus 1 over n plus 1. So meaning you have here negative u raised to 1 half over 1 half plus 1. Of course, 1 half plus 1 is 3 halves over 3 halves. Now, simplifying the expression further, 3 halves becomes, you take the reciprocal of 3 halves, that becomes 2/3. So negative 2/3 u raised to 3 halves, then plus c. Okay, so doing the representation again for u, replacing u with your original expression sine x, so you will having the expression negative 2/3 sine x raised to 3 halves, replacing u with sine x, then plus c. Okay, so again, the highlighted expression would be serve as the final answer for the given example. Okay, so as a final example, we have integral of cosine x raised to negative 5 sine x dx. So again, based on what we have done in example number 4, which expression in your given integrand would you choose to represent as your u? So the suggestion is you choose over the expression under which exponent? The one with the more complicated exponent. So the exponent for cosine x is negative 5, whereas the exponent for your sine x is 1. So choosing between 1 and negative 5, you choose negative 5. So the expression under negative 5, you represent that as your u. So we let u equal to cosine x. Derivative of u gives you derivative of cosine x is negative sine x derivative of x. Of course, in your original expression in your integrand, you do not have a negative sign, but what you have is your sine x dx. So getting sine x dx from negative sine x, we just simply multiply both sides of the expression for du and negative sine x by negative 1. So this becomes negative du or equal to sine x dx. Now, doing the replacement for u and du, we have cosine x is your u. So you have cosine x raised to negative 5. It becomes u raised to negative 5. Now, again, sine x dx becomes your negative du. So negative du. Now, negative du here is negative 1 du. Removing negative 1 inside of the integrand, writing that outside of the integrand, the expression now becomes negative integral of u raised to negative 5 du. Now, doing the power formula, you have negative of u raised to negative 5 over 1 over negative 5 plus 1 plus c. Of course, negative 5 plus 1 becomes negative 4 over negative 4. Negative becomes positive. So this becomes 1 over 4 u raised to 4. We have done the reciprocal for u raised to negative 4. writing u raised to 4 in the positive sense of the exponent, and writing it under or below the fraction in your denominator. So 1 over 4 u raised to 4 then plus c. So doing the replacement for u, you have 1 over 4. Since u is equal to cosine x, u raised to 4 becomes 1 over 4 cosine x raised to 4 then plus c. So we are done with the integral of the composite function and the chain rule. Now I am expecting that you will also answer the exercises. Try to notice in the exercises that you're already given the suggestion of which part of your integrand that you will be representing as your u. So in the first exercise, the expression 3 plus 2x is suggested as your u. Now what you are going to do is to, since you have u, what you're going to do is to get the derivative of u, and you try to replace the representations of the expressions in terms of u and du, and try to make use of the power formula or the properties of the indefinite integral to get the resulting integration. Now for number 2, the expression under the square root is the suggested expression that you will be representing as your u. And finally, in your third exercise, integral of x e raised to x squared dx, it is suggested that your u is your x squared. Now we haven't done any examples for the expression of the natural logarithmic base e. So in order to perform the integration for the natural logarithmic base e, try to recall the definition for the derivative of your e in your differential calculus. The derivative of e raised to x is simply e raised to x dx. Now, try to recall that. Try to look for the derivative of the pattern e raised to x in your differential calculus. Remember, take note. Derivative of e raised to x is e raised to x dx. Okay, so I'll be proceeding now with the applications for antidifferentiation. Okay, steps to determine a particular antiderivative or a particular solution for the reverse of the reverse derivative or antiderivative. First step is to find the general antiderivative of a given derivative function. Step number 2 is to substitute the given conditions to solve for the constant c. And third, the resulting function is called a particular antiderivative and is referred to as a particular solution. The solution becomes particular, it is because just like in step number 2, you will be looking for a particular value of the constant c. What we have done in the previous examples is that we look for the resulting integration or the process wherein we attach the plus c constant where c has no definite value. That is why it is called the indefinite integral. Now for applications, of course, the value of the constant c has a particular interest. So that is why in most applications we do not leave the value constant c without any definite value. There should be a process of finding a particular value for c. So this would be shown in the succeeding examples. Okay, so let's have the first application for antidifferentiation. We have rectilinear motion. Okay, so rectilinear motion is also a term referring to linear motion or motion along a straight line. This is actually an application for the integration in physics, wherein you try to recall in your physics, one of the major topics in physics is linear motion or motion along a straight line, which is of two types. One is along the horizontal and the other one is along the vertical. Of course, in physics, try to recall that the motion of a straight line motion along the vertical is the motion wherein the effects of gravity is being considered. Now, in your physics, this is called vertical motion is called free fall. Now, free fall is an idealized condition or an idealized model wherein the only force acting on our object for vertical motion is the force of gravity, which we do not try to include in the analysis for vertical motion the effects of air. So, since this is an idealized model, free fall states that you remove the effects of air resistance, meaning the only force acting on your falling object is the force of gravity, which is always acting downwards. Okay, so recall that if a particle moves along a coordinate line and its position or distance function is given by s of t. S represents our distance. S of t meaning represents that the distance is a function of time for specifying linear motion. Then its velocity and acceleration is given by the following differential equation. So we have v of t as your velocity as a function of time, which is equal to the first derivative of your distance as a function of time. So that is represented as s prime of t, or this is d of s of t over dt. Now for the acceleration is the derivative of your velocity. Now since the derivative of the velocity is the derivative of the displacement or the position, so meaning the acceleration is actually a second derivative of your s of t. So the formula for your a of t is v prime of t is equal to the derivative of v of t over dt. Now from the two expression for v of t and a of t, it is evident that from this equation that s of t is the integral of v of t dt. This one. And v of t is obviously the integral of a of t dt. Now, this is somewhat very complicated, but it becomes easier when we do the examples. So I suggest that you also do the examples in order to get a full grasp of the concept. Okay, so let's do the examples. Let's have example number 1. Okay, so determine the position function of a particle moving along a straight line with a velocity v of t equal to 4t plus 1, given that s is equal to 5 when t is equal to 1. Now, remember t here represents time, s represents position, and you are given the expression for your velocity v of t is equal to 4t plus 1. What is asked in the given problem is you are asked to get the position function. So meaning the answer is expected to be a function. Okay, so let's go over with the solution. We start off with our definition for s of t. Now s of t based on the above equation is s of t is the integral of v of t dt. So doing that, s of t is equal to integral of v of t dt. Now since we are given v of t is 4t plus 1, replacing v of t in our expression, we have the integral of 4t plus 1 dt. Now since this is an algebraic function, 4t plus 1, based on the properties of the indefinite integral, what we can do is to distribute the integral sign and dt among the terms in your algebraic function. So we will be having the expression for integral of t dt plus integral of dt. Now, of course, what we are left with the solution of the power formula. We have t raised to n plus 1 over n plus 1. So for our t dt, we have t raised to 1 plus 1 over 1 plus 1. And then the integral of t dt is t plus c. Now this results into 4t squared over 2 plus t plus c. Next is 4 divided by 2 cancels 2. You're left with 2. So you have 2t squared plus t, then plus c. Now, the solution does not stop there, since we are uh, asked to get a particular uh, value for the position for the particular position function given that s is equal to 5 when t is equal to 1. The expression 2t squared plus t plus c is not yet the answer since you do not have a particular value for c. Remember, our objective is to get a particular solution or a particular position function given that s is equal to 5 and when t is equal to 1. Okay, so from here, we have s of t equal to 2t squared plus t plus c. Substituting a particular set, specifically when t is equal to 1 and when s is equal to 5. S of t, when t is equal to 1, your position is actually equal to 5, so meaning s of 1 is equal to 5 is equal to, substituting the value for time in the expression, you have 2 1 square plus 1 plus c. Now of course 1 square is 1 times 2 becomes 2. Now this expression 2 plus 1 becomes 3 plus c. This is equal to 5. 3 plus c is equal to 5. Solving for c, we transpose positive 3 to the other side. That gives us c equals 5 minus 3 is equal to 2. Now this is a particular solution for c. Going back to our expression for s of t plus 2t squared plus t plus c, replacing c with a particular value, which is equal to 2, writing it again as s of t equals 2t squared plus t plus 2. This is a particular position function which has a particular solution. This is what is being asked for the position function for a given value for s and for t. Okay, so let's have another example. Example number 2. A ball is thrown vertically upward from the ground with an initial velocity of 49 meters per second. Assuming that gravity is the only force acting on the body, find the maximum height attained by the ball. Now, this particular problem is a bit difficult because you need to recall particular concepts in physics in order to arrive with a solution, a very coherent solution. Now, I have written down the following statements for needed statement in order to answer this particular problem. If you cannot recall these concepts, try to read your physics, particularly on linear motion and free fall, no? In order to follow on the solution eventually for this particular problem. Okay, so recall in physics that vertical motion is in idealized models is motion with constant acceleration. This means that A is constant and has a value of 9.8 meter per second square or 32 feet per second square. If you're making use of the British set of units, if you're using the international system of units, you will be using 9.8 meter per second square as the acceleration due to gravity. British units, for feet and second, you have 32 feet per second square for the acceleration due to gravity. Now remember, the pull of gravity always acts downward, therefore a negative sign must be included for the direction of the acceleration due to gravity. In essence, A should be written as negative 9.8 meter per second square, or A can be negative 32 feet per second square for the British units. Therefore, V of t is equal to the integral of A dt, based on our definition, is equal to A integral of dt. We have written A outside of the integral sign because A here is considered as a constant, since we are talking about vertical motion in idealized model wherein A is a constant. So since a is a constant, we write down a outside of the integral sign. So a integral of dt, you are only left with integrating the part of dt. Of course, the integral of dt is t, so v of t therefore is equal to at plus c sub 1. Now, I have written c sub 1 here as the first constant since we will be having a two-step solution for getting uh, the particular solution for the position. Now, why are we looking for the position for meaning s of t? It is because it is asked in the problem that you are asked to find the maximum height, and height is a position. So, meaning the objective for our problem is to look for an expression for the position function. Okay, so we have this. We are now at this part of the solution. We have found an expression for the velocity, and as a function of time, and that expression v of t is equal to at plus c sub 1. Okay, so next step is to find an expression for s of t. Now recall s of t is equal to integral of v of t dt. Now since we have already found an expression for v of t is at plus c sub 1, we can replace v of t here as at plus c sub 1 dt. Now this is an algebraic expression, so just like what is said in the properties of the indefinite integral, we can do the distribution of the integral sign and dt. So we have now this expression as a integral of t dt plus c sub 1. C sub 1 is a constant, so it could be written outside of the integral sign, c sub 1 integral dt. Now, of course, what we can do here to perform the integration is make use of the power formula. So the exponent of t here is 1. So you have t raised to 1 plus 1 over 1 plus 1. And the second part is the integral of dt, which is simply t times c sub 1. So we can write down the solution as a raised to t squared over 2 plus c sub 1t plus c sub 2. Now c sub 2 here is the second constant of the expression. Now, we can also write down that as 1/2 at squared plus c sub 1t plus c sub 2. Now, the next step of the solution is to find a particular solution which requires us to look for a particular value for c sub 1 and c sub 2. Now, take note in the given problem that at time t sub 0, meaning that at the very beginning, meaning at the initial condition for the ball thrown upward is that you are given an initial velocity of 49 meter per second at the starting point of the movement of the ball. So meaning at time t equals 0, the ball is at ground level. It is at the position 0. If you're going to put the position at the starting position at 0, the initial velocity at the initial position at the initial time is equal to 49 meter per second. So this means that the velocity at time t sub 0, making use of this expression, at plus c sub 1, the velocity is given as 49 is equal to a times t. Now a is the acceleration due to gravity. Since we are given the velocity as 49 meter per second are expressed in the International System of Units. Therefore, choosing between 9.8 and 90.8 meter per second square and 32 feet per second square, we make use of negative 9.8 meter per second square to be dimensionally consistent. Okay, so again, our velocity at time t sub 0 is equal to 49 meter per second is equal to the expression at plus c sub 1. Now a, based on the acceleration due to gravity, is negative 9.8 times t, which is 0, then plus c sub 1. Obviously, this part of the solution is 0, so you are left with c sub 1 is equal to 49. So we have solved now the first missing constant, c sub 1. Now, the next step is to look for for the particular value for C sub 2. Making use of the expression for S of t, which is 1 half 80 square C sub 1 t plus 14 plus C sub 2. Again, S of 0 for time 0. The ball is at ground level, meaning S is equal to 0. So S of 0 is equal to 0 is equal to the expression 1 half 80 square plus C sub 1t plus C sub 2. Substituting the values for C sub 1, we already found C sub 1, which is 49. We have 1 half 80 square is negative 9.80 square plus C sub 1t is 49 times 0, then plus C sub 2. Take note that this is results into 0. This term also results into 0 since this is multiplication by 0. Therefore, the result for C sub 2 is simply C sub 2 is equal to 0. Now, we have found a particular solution for C sub 1. We already found a particular solution for C sub 2. The next step is to go back to your position function and velocity function and replacing all the constants with the constants that we have found. Okay, so going back to your V of t. V of t is 80 plus 1. Now, C sub 1 here is 49, and A here is negative 9.8. Therefore, our velocity function is V of t equals negative 9.8 t plus 49. Our position function, which has the form 1 half 80 square plus C sub 1t plus C sub 2, now becomes 1 half negative 9.8 t square plus 49t plus 0. Now, of course, this results into simplifying further. Negative 9.8 divided by 2 gives you negative 4.9 t square plus 49t. We no longer add the 0 since that is only 0. Therefore, we have these two particular solutions for the given problem. Now, this is not the final solution since what is being asked in the problem is for us to find the maximum height. So of course the height referred to in the problem is position. So at the maximum height, this part of the solution, you need to recall your ideas in physics. Try to recall that whenever you throw an object upward, in this case our ball, what happens to the velocity as the object goes up is that the velocity becomes lesser and lesser, the velocity decreases, meaning eventually we expect that at a particular height, momentarily the velocity of the ball would be equal to 0. And that particular height wherein the velocity of the ball is 0 is actually the maximum height reached by the ball. So this means at the maximum height, the velocity becomes 0 temporarily since the velocity decreases for any object thrown upward. In essence, the velocity of the maximum height is 0. Hence, the time it takes to reach the maximum height would be given by V of t is equal to 0 at the maximum height is equal to negative 4.9 t plus 49. Solving for time, transposing 49 to the other side, 49 becomes negative, dividing both sides by negative 9.8, so we have negative 49 over negative 9.8. Negative 49 over negative 9.8 gives you 5 seconds. The time it takes for the ball to reach the maximum height, given that the initial velocity is 49 meters per second and the acceleration is negative 9.8, is 5 seconds. Now, since we have now the time, we can make use of the expression of the position function, substituting the value of time 5 seconds in the function. Then we can solve now for the maximum height. So since this is 5 seconds, S of 5 is equal to negative 4.95 square plus 49 times 5. 5 square gives you 25. Multiply that with negative 4.9 gives you negative 20.1. You can verify this using your calculators. Plus 49 times 5 gives you 245. 245 minus negative 2 minus 20.1 gives you 224.9 meters. So finally, we have S maximum as the maximum height reached by the ball, uh, where the ball travels 5 seconds from the ground, reaching the maximum height.